Okay, okay, so I'll start. Hey everyone, my name is Ashish, and this is gonna be our Intro to PyTorch workshop. This is supposed to be a part of a longer. Um, Jackie, you can hear me, right?
Yeah.
Okay. This is supposed to be a part of a longer reinforcement learning reading group. So last time I had asked few people, uh, last time I had asked everyone what they would like to do next. Would they like to see an algorithm first, or would they like to first know some basics to PyTorch? Okay. And then everybody said, let's do some PyTorch first, so that everybody knows what the competitions are about. And therefore, I said, let's do PyTorch. So today is going to be an introduction to PyTorch, and it's going to be hands-on. So you can do it on your own computer as well as I do it. And how it's going to be structured is that I will open a collab, and you guys can type alongside me if you want to. If you don't want to, it's up to you. But I will not type a lot of code, and I'll try to keep it as simple as possible. What we will do go through is like some examples of functions in PyTorch, some a regression example in PyTorch. Like it doesn't work as great, but it works or sort of, and then some then a MNIST example in PyTorch, how to achieve some good accuracy on digit recognition. So yeah, that's pretty much the plan for today. And if anybody has any questions at this moment, please unmute yourself and ask. Okay. Uh, so yeah, if it applies for the entire presentation. So if you have any questions during the entire presentation, please unmute yourself and ask. And I'll continue with the presentation. Okay. So let me just share my screen. Okay. Can you guys see my screen?
Yeah.
Okay. So I'll just take a tab and start coding. So this is what I have so far. And I'll give you the code at the end. So if you don't, feel free to type it. You can start looking at the code if you want to. So I should give you the code right now, I guess. Uh, Wait, I have to stop sharing and give you the code. So let me just share it on Zoom first, and then we can. I've already shared it before the reinforcement learning reading group, but I'll put it in the chat right now. So Jackie, you can share this one later on. This is the complete thing from last year. I made these slides last year as a part of introduction to TensorFlow and PyTorch workshop, but the PyTorch one never happened. So it's happening now. So Jackie, can you please share these to different people? And I'll continue and do a basic overview of this notebook.
Okay. Or do you want me to share it now or just wait till the end and then I'll
Wait
post it?
until the end because people
Or,
who are here can already access it through
yeah.
the chat.
Okay. Okay.
Yeah. Okay. Awesome. Um. So, all right. Well, let me share my screen again. Okay. So, as you can see, I have written down some stuff uh, for my own mental readiness so that I can start typing. But whatever I can't type, I will look over in a different collab notebook. So in general, we will first go through the example of calculating Euclidean distance using PyTorch, and then I will show how it's similar to NumPy. we create a regression model which does ax plus p. Then we will try to train it somehow. Like there's no neural network involved here, but it's kind of like a neural network. Like you can put it into a optimizer and try to train it, and then I'll tell you what the optimizer does and how it works, um, and then we will go through the MNIST training. So MNIST is this data set of handwritten digits. So for people who don't know, I'll just do a quick image search. Okay. Okay. MNIST data set. So basically in MNIST, there are like lots of handwritten digits of these types. And what is given is that every image is given to you at any time. Any image is given to you, and you have to classify it into one of the 10 digits, 0 to 9. So you have to create, and you have to say that, oh, this is from 3, this is from 5, this is from 7, this is from 5 or something. So it depends on whatever is given to you at training time. And then like after training, you have to say what digit it is. And that's a task of digit classification. And this is the data set. It's called MNIST. So any questions on the task, on the data set task? Okay. So if you have any questions in between, people who just entered, like let me know in between whenever you have questions. I'll try to answer them the best I can. And now I'll start do some coding, so you can start doing it if you haven't done it. If you haven't, if you want to do it, and so just start by uh, creating a Python notebook. Like how you can do is collab.research.google.com. You can go to this website, uh, and I'm not sure, is this big enough, Jackie? Is this visible? Can you hear me, Jackie?
Yep.
Is this visible?
Yep.
Okay, so you can go to collab.research.google.com at this moment, and when you go there, it will greet you with this page. So it will give you this page, and you can create a new notebook around here. You can see my cursor too, right?
Yep.
Okay. So they will greet you with this page, and you can create a notebook here. And then when you create a new notebook, you can start typing in the cells. So for this coding exercise, we will not go through any CUDA thing, any GPU. So, but GPU is easy to do. It's basically you can change your runtime type here. It's in runtime. So if you go to runtime and then change runtime type, then you can go and select GPU. And when you select GPU, you'll start running GPU. And how you would know you're running with GPU is that you can see this thing connect. It will allocate something, and then when it allocates it, it's in GPU mode. You will know. So this is the GPU mode, and it's allocated something. So I will not run it with GPU. I will just run it with CPU because it's good enough with the CPU as well. But GPU is pretty similar, and if you want to run it through using a GPU, all you need to do is like take your tensors, and like if you have a tensor called X, then you can just do x.CUDA, and this will put it on the GPU. Or if you have a model.CUDA will put it on the GPU. And then basically all you need to do is you need to put your models and your tensors on the GPU, and everything will work as normal. So that's a lot of detail, but let me just go back to CPU and start again. Okay. So first we will import torch and torch vision, and then we will import numpy as np. So Torch Vision is basically this library of image transformation techniques and data sets that PyTorch has. So you can just do Torch Vision and it will show you how what Torch Vision is. So Torch Vision package, I'll just show you the 1.6. So 1.7 is the most latest one, but it's you can see like there's a lot of data sets here. It just gives us access to a lot of data sets, models, transforms, and utilities. And basically you can see like what these data sets are like. So if you go to fashion MNIST, it will show you another data set which is like MNIST, um, but on clothes and everything. And then there is Celebre, which is a celeb data set. It's faces of celebrities, so that's celeb data set. Then there is extended MNIST, in which you have handwritten letters like A, B, C, D as well. So like there's many different data sets here that you can try out, but we will just try out the MNIST one, which is this one. So torch vision data sets are MNIST. Okay, let's start. So first, anybody has any questions here so that I can, before anybody wants to jump in, like anybody has any questions in getting to collab or starting a notebook or something so that I can answer that.
What I have just one question here.
Yeah.
For your torch vision, is there anything similar with TensorFlow?
In TensorFlow, well, TensorFlow, I think in TensorFlow the data sets are not handled that way. So TensorFlow, I haven't worked with TensorFlow in a long while.
Okay.
Like I've been using PyTorch for all my research since, but yeah, there's TensorFlow datasets. So I think the thing is that TensorFlow puts everything in TensorFlow except for like TensorFlow probability.
Yeah,
Except for that, everything is put in TensorFlow. So everything is available as TF dot something.
I see. Yeah. Okay.
So TF dot data is probably it, but I will, yeah, ready to use data sets, but they have like more things to do. Yeah, see, load MNIST, split train, shuffle files. So like same thing is in TensorFlow, but it's not in a different library. It's in TensorFlow datasets. Oh, okay, yeah, this is its own library actually. It's its own library. But usually, like what TensorFlow does is that it puts everything into TF dot something. So good question. So
Yeah,
any
got
other
it.
question?
Okay, thanks.
Anybody else? Anybody have any difficulties going to this website, or at least having like a, everybody has at least the uh, collab link that is shared on the chat, so you can try and open it. If it doesn't open up, like you can just see what I'm doing. Okay, anybody has any question related to collab, you can ask now. Okay. All right, so then I will just continue. So first we will import torch and torch vision, and then we will import numpy as np. Okay, so it will initialize, connect, and then it will run it. Okay, so you see the number 1. That means that this is execution cell 1. And then as you run more cells, you make mistakes, you can run them again, and then the cell counter increases. So you have import torch and torch vision, import numpy as np. And now we will try to calculate Euclidean distance between 2 points in PyTorch. So basically what we want is some kind of a function. Actually, first let me show you how to do it using numpy. So we will have, let's say there's a function g, takes in 2 points, point 1 and point 2, right? And what we want is Euclidean distance between points. So it's like, I'll give you an example. So let's say after I finish the function, I'll run this like this, 1 comma 2, this is a point. It's a list of integers. And then there is a point 3 comma 4. So how the distance is calculated is that you have the square root of x1 minus x2 squared plus y1 minus y2 squared, right? So you basically have to subtract x1 and x2 and y1 and y2. The points are given. So what you would do is basically first you will take x1, x2, x1 y1 and x2 y2. Since these two are vectors, you can subtract them and you'll get x1 minus x2, y1 minus y2. Then you can do squared. Then you have to do square. Oh, wait a second. Yeah, then you can do a square. Square of these two terms. So basically a square of x1 minus x2 and then square of y1 minus y2. And then after this, you can add them. And then you have to take a square root of the thing you added. That's the distance, right? So how will you do it here is basically you'll take 0.1 and 0.2. You'll take 0.1 and you'll say, you'll first convert it into a numpy array. So let's say 0.1, 0.1 is equal to numpy dot array 0.1. 0.2 is equal to numpy dot array 0.2, and then you will have distance is, we'll do it one by one, but distance is 0.1 minus 0.2. First you do this difference, then you square it. So to square it, you do numpy dot square, and then after squaring it, you have to add it. So numpy dot add. So you squared it, added it, and then you take the square root of it. So numpy dot square root, and then you return the distance. So hopefully this when this runs, it produces some distance. Okay, let's see what happened. Invalid number of arguments. Okay. Okay, let's just do it one by one. 0.1 minus 0.2. What does that return? Okay, that's good. Then numpy dot square. What does that return? 4, 4. Good. And then numpy dot sum. What does that return? 8. And then numpy dot square root. 2.8. Okay, I think I did that. Okay. Basically, this is how you would do it in NumPy. You'll convert these two to a NumPy arrays, and then you'll take 0.1 minus 0.2, and then you square them. 0.1 minus 0.2 will give you x minus x2, y1 minus y2. You square them, and then you'll add them using numpy.sum, and then you square root them. So that's how you get the square root of x1 minus x2 squared plus y1 minus y2 squared. So any question in this example before I start going to PyTorch? Okay. So let's do this equivalent example in PyTorch. So let's call the function f 0.1, 0.2, and it's similar. So it just goes 0.1 is equal to torch dot tensor 0.1. 0.2 is equal to torch dot tensor 0.2. Okay. So that's how you converted it to tensors, and basically everything is same. All the functions that are available in NumPy are also available in PyTorch. So all the operations you can do in NumPy, you can almost always do them in PyTorch. So that's how, in general, PyTorch is structured. It's like a NumPy-like library, but allows you to do stuff on the GPU. Okay, so first let's just do 0.1 minus 0.2 and let's see what this returns. F okay, it runs tensor minus 2 minus 2. Okay. So to make it CUDA, like all you need to do is to do this CUDA. Whatever you have, whenever you have a tensor, you just do a dot CUDA. It makes it a tensor on the GPU. Okay. And then after you have done that, you have to do a square. So not numpy, but torch dot square. And squares it. Then you torch dot sum. Okay. And then torch dot square root. Okay, so we got the same number. It's basically the same thing, except that this in PyTorch, the benefit is that you're allowed to work with tensors and in GPU. So there's more functions available than NumPy. Okay, any questions so far as to what we are doing? And
Is there any speed difference using with NumPy and Torch?
yeah, when you like in general, like you won't see the speed difference when you put it on CPU, but when you put it on GPU, you'll start seeing lots of returns because GPU will parallelize everything. Does that answer your question?
Oh yeah, thanks.
I have a question.
Yeah.
I have to put dot CUDA in every assignment.
I'm sorry, what?
I have to put dot CUDA in every assignment when I
No.
use
When you create the tensor. So when you create the tensor, you can put it dot CUDA here, and that's it. Like you have to start whenever you create. Every assignment, every time you create tensor, you have to put a dot CUDA.
Okay.
And then when you have a model, also you can put a dot CUDA. So it's at assignments and at model assignments. Okay. Okay, so let's just move on. So let's just try to create a regression model, right? So basically, let's see how we can create this simple model, ax plus b, and how to train it. But this is not this is not entirely a neural network because there is no neurons and everything. It's a very simple regression model that we are trying to train using an optimizer. But like there is no complicated functions here, so it's not gonna do as well. But let's try to see and we'll see how we'll do it anyways. So let's call this regression model, right? And then in PyTorch, basically to create a module, what you have to do is you have to take torch dot and then dot module, and you have to create a subclass of that module. So it's always like this, and then you can initialize it. Definite. I'll just create some spaces for that. Okay, and then every time you have to super initialize. Okay, so after this you can write whatever you want in your model. So what you do is basically you have to define two functions. There is a function called init and there's a function called forward, self and some input. So in regression model, basically what I'm trying to teach you here is that there's something called as a parameter in PyTorch. And how a parameter works is that it's different from a tensor. So what happens is that when you have a tensor, you can have this attribute called grad, requires grad. So it basically creates, it's how Autograd works. So I'll tell you what Autograd is. Okay, so in general, Autograd allows you to differentiate things for all operations on tensors. So what this means is that whenever you do import torch and you try to do whenever you start a tensor, whenever you create a tensor by doing requires grad equals true, like if you have this attribute set to true for any tensor, then it will start tracking your computation. So like if you have a tensor, then it will just say requires grad equals true. And then when you do x plus 2, now it is going to track your operation, and it will say x plus 2. Now that's an operation. So I will remember this operation. Then you can see the function that it's going to use to like go backward. So what it's remembering is kind of the reverse, or somehow how to propagate values for these things, like just like in neural networks. If you know how to do a forward pass, the Autograd is remembering how to do a backward pass or how to do back propagation. So if you do z is equal to y into 3, and then you do z dot mean, then if you print z, so you already have done an addition operator on y, which was here. Y is equal to x plus 2. So now it has two operations that is tracking. Y into 3 is what z is, and z's mean is what has been printed. So it's going to print this, and then out is another one. So it's going to create two tensors. And whenever you want to create a new, this is what it's doing. It's creating a computation graph. So like whenever you do any operation on any tensor, it's going to create start a computation graph, and it will remember these operations that you did, so that it can do the backward of these operations when you're trying to remember or learn things. So for learning values, this is what Autograd does. So any question in what Autograd does? So it's the syntax is pretty simple. Basically, what is happening is that every tensor has this thing called a gradient function, and when you try to do a requires, like you set requires grad to true for a tensor, it will start remembering what you keep doing to that tensor, and then eventually you can look at its grad function. It will tell you that there's a function that it can use to back propagate from that node to the previous node, and to the previous node in the stochastic in the graph, right, in the computational graph. And then if you want to do a back propagation step, which is how neural networks learn. So basically, how neural networks learn is that they will do a forward pass, and then they'll do a backward pass. So in general, very simply, that is how neural networks are learning. And what Autograd is doing is that it's remembering what you're doing at every step, every matrix computation you're doing. And then when you just call a dot backward on it, it will do a backward pass. So that's what roughly gradient updates are doing, and that's what it's computing. Every tensor has associated with it a gradient value, which is what it needs to change in its value to update itself over time. And this is according to a loss. So whatever, you have to take a loss function, and you have to do a backward on the loss function. That's how it's learning. Okay, so any questions here before I move forward? Okay, so let's just go and do the regression model. You'll understand more. So let's just do self.a is equal to torch.nn.parameter. And then data is equal to it's torch, so let's say zeros. Data is what you want to initialize it. So zeros is a function, and you're creating an empty shape. And then data is this, and requires grad is true, because you want to learn this regression model. And then same thing with B. Okay, and then this is basically return self dot a into x plus self dot b. Okay, and yeah, there is this function called wrapper, which you can use to represent things. What it does is that it just whenever you create, whenever it gives you the instance, you can print that instance. It will show you um, the different things in the model. So let's say I want to see what the values of the things are. So it will return, let's say return then the value of A. So let's say value of A is percent F, then B is percent F. Sub.A, sub.B. So any question in this code? We are just creating two parameters, and parameters are tensors associated with modules. So whenever you have a module and you have a parameter, it makes sense to use a parameter rather than tensor, because parameters can be associated with the module, and then when you assign requires grad equals true, it can start remembering whatever you're doing and create your computational graph. And then when you have created a computational graph, you can do operations like this operation. It will remember what you did. You multiplied it and you subtracted it. So it knows the inverse of this operation. It knows how to propagate the gradient back, basically. Okay. And then okay, it shows you A's values is this, B's values is this. Once you have a model, so that's what repr is doing. Representation is what it's giving you. It's a string representation. Okay, any question here? If you want to do a forward function, basically you have to pass, all you need to do is pass in an x. So I will pass in a tensor. So I'll pass in a torch.tensor of say a value of 0.5. And then what we'll do is 0.5 times a plus this, which is equal to 0 plus 0, which is 0. So tensor 0, gradient function is addition backward. That's what it's doing. Okay, let's do some, any questions here? How to use the model and how, what these different functions are, and how to do, what is a wrapper, and what is a computational graph, and what is a requires grad, or any kind of question regarding that.
When you are writing torch dot zeros, it's like, I'm guessing it's an array, right, of zeros. All the values are zero.
Yeah, the thing.
What is the
Yeah,
size?
yeah. So this size is empty, which means it's a scalar. It's a number.
Oh, okay. So that means only one value vector.
Yeah, if you want to have a shape of 3,3, it will create a matrix of size 3,3.
I see.
But if you create something like 1, this is basically, it will create a vector and it will put a number 1 in there. So I don't want any vector. I just want number, and that's it. That's why I didn't put anything.
Oh, so when you put this one like this empty, that is you don't put zero, right?
Yeah, it's gonna create a number 0,
Okay,
and that's just a number. It's just not gonna create a vector.
I see. Okay,
It's a scalar. It's not a vector. When you want to create a vector, you have to provide a first index. So whenever you provide any index like 5, 4, then it will create an array of size 4,
right.
and that's a vector. But if you don't want any vector, you want a scalar, then you can just do this.
I see. So it is similar to the np dot zero, like in the same.
Yeah.
Okay.
Okay, good question. Any other question? Okay, let's move on then. So let's first do some ground truth function for regression model. And in general, what we want, let's say we want to do this ground truth function, which is def ground truth. So what are we doing here is basically we are taking x and we are creating a ground truth function, which is, let's say, 2x plus 7. So this ground truth function is basically what we want to learn in these parameters a and b, and somehow we want to use PyTorch for it. So it kind of learns, but let's see how you would do it, how you would go about doing this. So let's first define how to do a loss function. So basically for loss function, you will use something you have like in PyTorch, you have lots of loss functions. So you can just search for PyTorch loss functions, and then you'll see like lots of loss functions. But what I'm going to use is called mean squared error loss. So it's like the Euclidean distance, but it's first it's uh, mean squared error. Yeah, MSE loss. Yeah. So it's like the Euclidean distance, but what it does, it's calculating the mean of the squared errors. So it takes a square error, squared L2 norm, and then it takes a mean of that. So I'll use this as our reference, and you can see that in PyTorch documentation is really good because they have like lots of examples for everything. Well, most of them have, but I find that PyTorch documentation is very clear about examples. Okay, so I'll just do torch.nn.mse loss. And then what I can do is I can do a loss between model, what the model gives me. So let's say a model gives me for torch or tensor 0.5, that's the input to the model, and it predicts a value. It gives you this value, right? And then the second value is ground truth. So ground truth for the same value, let's say torch.tensor. So loss function is gonna return something. The ground truth is not defined. Okay. So what it did was it did a mean squared error between these two terms. And the first term was what the model, what we sent to the model and what it returned. And the ground truth is what we wanted to learn. So that's how usually machine learning model works. Like you have an input, and the input is passed to a model. The model predicts something, and then you have to compare it against some ground truth value. That's how supervised learning works. And in our case, supervised learning, we want to do, we simply want to do like learning these parameters of this regression question. So we want to learn what this parameter A is, what this parameter B is for some ground truth values that we have. Okay, so let's just try to train it. Now we know how to, this is a loss function and there's a grad function associated with it. We can just do a dot backward and we'll learn something. It will propagate some gradient. But that's where optimizers come into the picture. So optimizers can be created simply. So optimizers are also available. You can just Google optimizers and it will show you some optimizers. Okay, so everything in Torch optimization is basically in torch.optim. So it just basically tells you what optimization algorithms are there. But in general, the most common ones are SGD and ADAM. I'm going to use both of them today. So SGD is basically stochastic gradient descent. And what it does is, if you want to see what the optimization step is, basically you can see the implementation of SGD. So implement stochastic gradient descent, and it's based on the formula. Nestor momentum is based on the formula. Okay, that's different. But in general, what is happening is that implementation goes like you have to subtract certain value from, like you have to subtract a gradient with some learning weight from some parameter value. So like I'm not going to discuss too much about how it works, but think of it like a black box which helps you learn something. It's a black box which will help you learn something. So how to use it is basically torch.optim. You create this instance, and it needs two things. First of all, it needs parameters which it needs to learn. So parameters are model parameters. So model.parameters. And the second thing, it needs the learning rate. So I'll use a learning rate of 0.1. But we don't need to use a learning rate of 0.1. You have to like play with the parameters and figure out what works for you. So that's hyperparameter tuning for you in machine learning. And then basically what I'll do is I'll create import for like I do 20 epochs of training. So for I in range 20. Okay. The first step is you do a model.zerograd. Zerograd, basically what this will do is take the model, take all its parameters, and make sure that their gradients are set to 0. So gradients are what are computed during backward pass. Then you will take the optimizer and you have to set the set all its gradient to 0, because optimizer is also kind of like a model which has its own parameters. And then you have to do some loss function. So let's say this loss is loss function. Loss function is let's say this is loss. So let's say this is, let's call this a loss function. Okay. Okay. So loss is loss function. And then model torch.tensor. And then some value, let's say 0.5. Let's put it x, right? Let's put x. We'll decide what x is later. But model, what the model predicts, and the ground truth of the same value. So basically, what the model predicts and what the data point we have, we are just going to like in general, like in supervised learning, we are given x's and y's, right? So x is what is passed here, and y is 2x plus 7. So when you have x, you pass it to the model, it gives you a y hat. So it produces a y hat when you pass it to the model. Y hat is basically the model x. And then you have y, which is the true value, which is 2x plus 7. So that's a ground truth. So ground truth of x, no, not x, dot of x. What is x? Let's say it's a random number. Like let's say random np dot random dot rand in rand np dot random dot rand. Let's say. So it just generates a value between 0 and 1. And then do a loss dot backward. Oh, backward. This will basically propagate the loss backward. It will compute the gradients, move the gradients back in the stochastic, in the computational graph, and then it will change the values of the parameters. So it will adjust the parameters little by little, and then you will do this multiple times so that you learn the parameters. And then once you've done that, you have to update the parameters of the optimizer. You have to do optimizer step. These are the only steps you need to know. You have to zero the gradients, then you have to compute the loss, and then you have to do a loss dot backward, and then you have to update the optimizer. And then when you have done that, you will have adjusted your parameters of the optimizer and the model very so slightly, so that it's going towards the correct, it is minimizing this loss. And that's how you use an optimizer. So in general, let's run this and see what the values are. So let's just do 20 epoch %d loss %d. Epoch number is I plus 1, and loss is loss dot item. So basically, if you have a tensor scalar, that is, it's not a vector, then you can do a dot item and it will give you the actual value of the tensor. So, okay, let's just run this. Okay, it starts with a 63 and then it goes down and down and down and down. So it goes until the very end. Okay, let's see what the values are. Oh, this is all integer. I should have started by doing non-integer. Anyways, let's see what the values are. So the model is, okay, so basically it learns model values at 3 and 6. And we had like 2x plus 7. So that's pretty close, not that bad. Okay. Oh, I did a %d here. I've chosen percent. So that's how it's not going. Yeah, because let's run it again. Yeah. So you can see this, these are actually float values and the loss decreasing over time. And then you print the model, it will show you the model values. Okay. Any questions up till this point? After this, I'll just do the MNIST example. Okay. No questions up to here? Okay. So now we'll do some MNIST training with 2 training layers. That is, it's a neural network such that you pass the input. And then it's like this. You take an input of size 784 is a size because actually every image is a 28 by 28 image, and there are many images of this type. So k comma 28 comma 28 is what the image size is, but we will multiply these two, and 28 times 28 is equal to 784. So basically we will have many vectors of the size k comma 784, and then we'll basically pass it through a neural net. And how a neural network works is that first it passes it through a linear layer. We'll use a linear layer. So the linear layer has weights like it has a matrix of size 784 plus 100. So this becomes k comma 784 times 784 comma 100. So this becomes k comma 100, and then you're adding a bias of size 1 comma 100. So it stays k comma 100. And then you have k comma 100, and I'm multiplying it with 110, and bias is 110. So it's going to become k comma 10. And so basically now you've transformed your input of k comma 784 into an output of k comma 10. And this output is basically your 10 class classification. So it's basically if it's digit 3, then the value of the output of 3 should be high. If the value is 5, if predicting 5, with the value of 5 should be high. So that's you have digit 0 to 9, and you have 10 numbers, and so it will produce 10 numbers, and whatever number is the highest, we take that as the highest value. Okay. Any questions so far? Okay. So let's just do this, and we'll first create a transform. So basically, in Torch Vision, a transform is some kind of image operation, and Torch Vision has these great library of transformations, and then you can use these transformations without even needing to implement many of these transformations. So one of these transformations I'm going to use is basically it's you have to, for any transformation, you have to do a transform that compose, and then compose will basically take your transformation. It will compose a bunch of transformations, a list of transformations. In the transformation I'm going to use is Torch Vision dot transforms dot tensor to tensor. So what 2tensor does is basically it takes an image, it converts it from a pixel value, which is between 0 and 255, to image values between 0 and 1. It converts it to float, and it makes it a tensor, Torch tensor. So I don't have to worry about it being a tensor. Okay. Let's create 2 data sets. So in PyTorch, the data sets are in Torch Vision data sets, like we saw. And so basically, train data set is equal to Torch Vision data sets .mlist. And then we need a root directory. So where do we want to place these files? I would download these files. And then we have to say, do you want a train thing or something else? And then transform. So you can, in Colab, you can see these parameters, which helps you like remember what to type next. Transform is equal to transform. And then download is equal to true. And we want to also download a test data set. and then test data set of train is false. So we have downloaded a train and data set, train and training data set. If you want to see the files, I think it should be here. See mnist. That's where your processed and raw images are. It's all it's in a model file, so you don't have to worry about it loading it. It's already loaded for you. Okay, and then we have to create something called as a data loader. A data loader basically is this thing which you can just call for. What it will basically do is it will take your data set and it will generate batch size mini batches of like mini batches of your data set. So if you want to have mini batches of size 64, then you can sample randomly from it and then not worry about what's happening. So it's pretty simple. What you will do is you have to create um, train loader and a test loader. Let's train loader will be created on a train data set. Train loader is torch dot utils dot data loader train data set that size. Of course, like I don't remember all these things, but sometimes I'm like when I'm typing, it shows these things and I can see what to type. But in general, like these are the very minimal things you will need to create a working MNIST example. So I have two loaders. I have a test loader and a train loader. And as you can see, batch size is this. So we'll just create this on the test and train data set. Okay, now I'll show how to use it. Basically, okay, we may go like 5-10 minutes over time, but I'll try to finish the example. It's not that long. It's almost there. So to use basically train and test loader, what you have to do is you have to take your train loader, or you have to convert it into an iterator of train loader. And then when you do an iterator, you will see that it becomes an iterator, and then you can call a next. If you want to call a next, it will give you examples X and Y. Okay. But if you don't want to call it X and Y, you can do this like X comma Y in iter train loader. And because it's an iterator, it will go through and iterate through many instances of this train loader, and it will not repeat examples because like usually it doesn't repeat examples. So we have X and Y. Let's see what X and Y look like. So X, we just already did this. So let's show what X and Y look like. X looks like tensors of zeros and ones. Okay. What does Y look like? Y looks like these labels, right? 0 to 9. So this is the ground truth. And if you want to see X, basically, if you do torch or tensor, sorry, it's already a tensor. So if you want to see the size of it, so we can do X dot size and then Y dot size. That will show us size of these two. So one of them is 64, 128, 28. So it's a mini batch of size 64, and every image is dimension 1, 28, 28, and the labels are all in this dimension 64. Okay, and then if you want to see what the values are, like we really scale them to 0, 1, then you can just do a torch dot min of X and then torch dot max of X. So it'll show you the minimum maximum values in X. These are zeros and 1, like we said. That's the function of this 2 tensor. Okay, let's just now try to plot a random label, and basically how to do that is we need to show import matplotlib pyplot as plt, and then I'll do plt.ensure. We take X, which you just created. X is this image x dot size is, you want to plot a simple image. So you have to take x, let's say image 0, but it will create a tensor of size. This will create a tensor of size 128, 28. So we need to squeeze it. Squeeze will remove this one dimension. Squeeze removes all the one dimensions basically. And then squeeze and then convert it to numpy. So that is how it will show this. And then we can just print the x0's label, so y0. So it's 5 and the tensor 5. So it's basically the digit 5 and the label of this is 5. Ground truth is 5. So what we need to do is create this classification model now. So it's very similar to the, like I've already outlined how to do this, but I'll do this quickly. Basically, you create a classification model, and it's a subclass of torch.nn.module. And then you have this init function in which you do super.init. And then you have this forward function in which you do self.x, self.x. Now to fill these two functions, right? So what we need is a parameter for this, a parameter for bias, a parameter for this, a parameter for this, bias for this. And then these four things are what we need exactly. So self.w1 is equal to torch.nn.parameter. Data is equal to torch.zeros. And size is 784, 100. And the required style is true. Yeah, I accidentally got input this one. Then this is bias 1. This is W2. Bias 2. Okay. 74 cross 100. This is 1, 100. Then this is 100, this is 100, 10. And this is 1, 10. And then basically I'll have to do initializations. So if you don't want to initialize, then it will not learn because everything is zeros right now. So we need to start by initializing it randomly. So either I could do random here, which will initialize with random variables, or I'm going to do a normal initialization, which is you can do torch.nn.init, and then you can do a normal initialization. So bias 1, weight 2, bias 2. So this is how you create it. But let's see how to do this forward. So we'll take x. X is if you know x is something like 64, 1, 28, 28, right? So you'll take x. You will view it as x dot shape 0. So we are at 64. I want to turn it to 64, comma 784. So I can just use this in 784. Right. Or if you don't want to calculate the dimensions, you can just do a -1 and it will calculate the dimensions for you, 1 to 28, 28. And then once you have this, you can do x is equal to torch.mathmal. X into w1 plus self.bias1. And then you have to do a ReLU on top of this. Self.ReLU. Okay, what is a ReLU? ReLU is a nonlinear activation function. So basically you have a linear layer. a ReLU, a nonlinear activation function, and then you have a linear one. So torch dot dot ReLU. You can look up the activation functions as well. At this point, I'm just trying to code this example and show you that it kind of works. Okay. Okay, and then you return X. Okay. And then you can do model is equal to classification model. Okay, so hopefully there was nothing wrong here, because what we did was just converted 64.128.28 to 64.7.784, and then we did a x dot w1 plus bias 1, and then you did a ReLU. So it converted it from k784 to k100, and then we take a k100 and we multiply it by weight 2 and bias 2 after doing a ReLU, and then return it. Okay. Okay, so now it's pretty simple. Let's just let's just to show how to do a cross entropy loss. Basically, if you just like the MSE loss, you have a torch dot nm dot cross entropy loss. We pass the input. We already have the input because we just did an example of an iterator. And then you can see the loss. What happened? Iterator. Training data. Okay, what am I missing here? What, I have the code. So. Yes, I think the rest of the parts are simple. I think we are going overboard, so I'll leave this part and show you how it actually looks, because I have to debug it right now. But in general, what happens is that you have a classification model, and you can pass it, you can forward it to an example, forward it to something, forward it through the model, and then you get these values, which are 10 values, and then you have these 10 values, and you have a cross entropy loss. The y is basically what the iterator was showing, and then once you have those, what you have to do is basically create an optimizer, and then just like before, you have to do a model.Zerograd and optimizer.Zerograd, and you have to do a loss dot backward, and then you have to do an optimizer step, update the parameters of the optimizer, and then you can calculate, and you can see that the loss decreases in value. And then you can also try to predict the value of the thing using model X, and then you can show what the best logit is, what the best prediction is, and it matches many of the times. So uh, and I also computed the accuracy, and you can see it's 96% after you complete it. But if you run it with the blank model, it goes to just 10-12%. So it's basically this model works. It's I think we are over time, so I'll finish on this note. So any question in the like in the topics that I mentioned, like you can run this code. I've already given you the code here, but in general, like any questions about different thing, anything in this presentation? Okay, so I'll stop sharing my screen. Okay, so that's pretty much it for now. And yeah, we'll cover next time in the reinforcement learning reading group, we'll cover the next topic, which is A3C. So yeah, and yeah, like for the reinforcement learning reading group, we still have a competition for DQN. So I've already given the code for that. If anybody needs to get the code for that to start practicing on that, they can just contact me. Thanks again. All right, Jackie, I'll stop recording.
Okay, sounds good.